As for our next presentation about machine learning, it's an early preview. It's still currently in development. We are testing things out performance-wise and just simply how it's going to work, what's optimal for our users, and things may change down the line. But it's still interesting and still useful to understand how we are seeing the use case and the feature right now.
Hello, my name is Alex, and today I want to talk about two new features: anomaly detection and baseline monitoring in Zabbix 6.0. Nowadays, every company relies on various network devices, virtual machines, hardware servers, and many different applications to run their business. And if there is a way to throw in more hardware or software to solve a particular problem without increasing IT staff, businesses quite understandably choose to do so. And naturally, the more monitoring entities mean more and more metrics. The IT environment itself may change quite rapidly due to some unpredictable factors, and often there is not much time for in-depth assessment and analysis. For example, the global pandemics made many companies shift focus to better VPN support and increased external traffic. New paradigms and new approaches to IT operations create new monitoring challenges. Things like container orchestration, cloud services, advancement in database technologies, complicated delivery pipelines are going to keep sysadmins and DevOps engineers busy in the foreseeable future. And all this means that each individual monitored entity, be it a hub or a PC or a new application, gets less and less attention from the monitoring professionals. This also means that it's becoming increasingly difficult to keep track of all individual alert thresholds. In modern dynamic environments, you don't care about what is the norm for, say, a CPU load average in a group of application servers. You just want to be notified if there is anomalous behavior. So, in other words, it's difficult to get a good alerting with a proper signal to noise ratio manually. That's why we need to automate it. This means that we need to make Zabbix constantly learn what is the norm. So, what actually is machine learning? There are many definitions, but we particularly like this one. It is a field of study that gives computers the ability to learn without being explicitly programmed. Some people may immediately imagine complicated neural networks whose black box nature magically finds any sort of anomalous data. While nowadays such algorithms are very common, we wanted to start with tools that are transparent and easy to use. By this we mean that the tools must be simple to configure. Configuration should be as frictionless as possible. Ideally, a handful of trigger functions with only a few parameters should cover most of the use cases. Easy to understand. By contrast with neural networks, our approach is transparent and can be understood by anyone with a basic knowledge of arithmetics. Easy to verify. The algorithms and formulas we use are very well known and documented, and results can be easily verified by external tools. So, our main goal is to provide automated alerting, or smart triggers if you will, that can analyze historical data and answer the question whether there are values that are not as normal as the others. There are two main directions for such analysis: anomaly detection and baseline monitoring. Anomaly detection works by going through the historical data and finding outliers, values that are located too far from the rest of the dataset. A baseline is a value that is calculated from a set of historical values that fall into specific calendar periods. So we get the baseline and compare it to some other values. For example, the average over the last period. Alternatively, we can gather the data from specific calendar periods and calculate deviation, which then can be used to check if the current value is within a specific number of deviations. More on this later. Let's have a more detailed look into anomaly detection and see how it's implemented in Zabbix. Once again, anomaly detection is the process of identifying unusual values, called outliers, in history where the majority of values are considered to be normal. This is a pretty important point to keep in mind. If the majority of your data is anomalous, the algorithm has no way of finding this. It's also worth mentioning that anomaly detection, being a long-term analysis tool, works best on long-term segments of data. So in Zabbix, anomalous functions work with trends. There is a number of approaches to finding outliers in time series, so some of them are simple and some are very complicated. We choose STL decomposition as a balance between good results and simplicity. STL stands for seasonal and trend decomposition using LTS. LTS is a mathematical method of curve smoothing. Let's take a closer look at what is decomposition. Consider this example. This is a network traffic graph from a small mail server. As we see, there is a couple of larger traffic spikes and quite a few smaller but noticeable fluctuations. If we wanted to create a universal trigger to handle such situations, we would need to evaluate possible absolute thresholds or percentages carefully and then do some time-consuming trial and error testing. Let's see how decomposition works in such common cases. At the point in time t, which is horizontal axis, the graph value is yt. So the idea is to split yt into three components. A trend component that shows us a big picture of where the graph is going, a season component that shows us a repeating pattern, and a residual component, which contains everything that is not included in the first two components. The sum of these components must give the original value yt. This can be expressed with a simple formula. The steps are the following. First, we apply a smoothing algorithm to the original curve, and this way we get a trend curve. The smoothing algorithm should be resistant to any sharp value changes. Second, we subtract the trend curve from the original curve and split the result into seasons. Third, we average all values whose position is the same in the season's time coordinates and get the season curve. The final step is to get the remainder array by subtracting corresponding points of seasons and trend curves from the original one. The decomposition result looks like this. The first graph is from our original example. The second graph shows a trend. As you see, the LTS algorithm used by STL does its job very well and ignores the spikes and sudden value changes. The third graph shows seasonality. You can see a clear repeating pattern on this graph. The bottom graph, which contains the remainder of what's not in the first two, is our main subject of interest. As you see, the vast majority of points are grouped around 0, which shows the normality. But there are few points that are way more distant from 0 than the others. These are good candidates for anomalies. Whether the specific point is considered to be an anomaly or not can be expressed in a number of deviations. Let's briefly see what is a deviation. Intuitively, we know that averages of large datasets rarely show the whole picture. A deviation is a measure of data variability. It answers the question how far is a typical value from an average value in a dataset. There are many ways to calculate a deviation, but the general idea is to get an average distance to a mean of a dataset. Many probably are familiar with this picture. It shows a so-called normal distribution, and it's very common in statistics. The horizontal axis is a number of deviations and the vertical is a percentage. We see that statistically the vast majority of values are less than 2 to 3 deviations away from the mean. We can use this observation to detect anomalous values. As I already mentioned, there is more than one way to calculate a deviation. Zabbix supports the two most used formulas, standard deviation and median absolute deviation. There are standalone functions for these calculations available since Zabbix 5.4. You may find them useful for your own analysis. But these methods can be switched between anomaly detection function I'll tell about in a minute. Now, when it's clear that what is STL and what is a deviation, it's easy to merge these methods to create anomaly detection algorithm. First, select history for the period from trends tables. Second, apply decomposition and keep the remainder part. Third, calculate a deviation from the remainder time series, then select all points with values exceeding the threshold number of deviations. Now let's have a look at the actual trigger function that does all the job. Even though anomaly detection is a multi-stage process, we have packed all stages into one convenient call. The function accepts many parameters, but there are reasonable defaults for most of them. The function returns a number between 0 and 1. It is a ratio of a number of anomalous points to a number of points. I'll not go into much detail about each parameter as all these are described in the manual. Let's just have a quick walk through these parameters so you get a general idea. First, it's worth noting one thing that may not be obvious right away, is that the function accepts 3 periods and these periods must be chosen carefully. The first one is the evaluation period. It's the actual period we do decomposition for. It is expressed in standard calendar units the same way as in other trend functions. The second one is the detection period, the period we report anomalies for. It uses the same units, hours, days, months, etc., but without a time shift. We need this period because typically we want to analyze the longer period into the past to get more accurate results, yet we are not interested in all anomalies for that long past period. The third parameter is a season. It is the length of season fed into decomposition algorithm. Let's see how it can be used in a trigger. Here is a concrete example of possible usage. It decomposes the period of the last 30 days and reports anomalies that occurred in the last week. We selected 12 hours as a season because we know that the outgoing network traffic varies significantly between days and nights. We use the median absolute deviation function as a deviation calculation algorithm and use 3 deviations as a threshold to tell whether the value is anomalous or not. Please note that 3 and MAD are the function default values. This should be reasonable defaults for the majority of use cases. Since the last 2 arguments are default, the call can be rewritten in a simpler way by using just an item and 3 periods. Now let's talk about some caveats. Firstly, let me remind it once again that this function only works with trends. It's not meant to be a first responder in case of some urgent disasters. Secondly, you will get good results only for data that has some seasonality in it. So if there are no repeating patterns in your data, this algorithm will just not give you reliable results because decomposition will not work properly. And the last thing to remember, the season parameter, which is a function's first argument, is expressed in seconds. Of course, you can use standard Zabbix suffixes like 2h, 30d, but it's translated to seconds internally. Now let's look at the new baseline monitoring functionality of Zabbix 6.0. In a broad sense, we can define a baseline as a value derived from the past measurements and use it for comparisons with the current one. In Zabbix, we narrow this definition down to a comparison of a value derived from an average over multiple calendar periods of the same length. Let's have a look at the main properties of baselines in Zabbix. To work with baselines, we need two notions, period and season. In this context, the word period means the actual time frame we use for calculations, whereas season is a time segment where the period is located. Baselines are calculated from calendar periods. For instance, if today is Tuesday and we want to calculate a baseline for a previous day over the past 4 weeks, then we will take an average of 4 Mondays each per week. Other things to keep in mind: periods are not absolute. These are values linked to the current time. And given that baselines are designed to be useful as a long-term analytics tool, they work with trends tables, not history. Anyway, a picture is worth 1,000 words, so let's see how periods and seasons are laid out on a timeline. Here is an example of how Zabbix will select periods if told to calculate the baseline value for one day taken from the previous 4 weeks if today is Wednesday. If you are familiar with relatively new trend functions, such as trend average, which have been introduced in Zabbix 5.2, you will find a similarity in terms of how these calendar periods work. Now let's see concrete functions to work with baselines in Zabbix. Baseline WMA takes all periods that fit into seasons, calculate an arithmetic mean for every period, and then calculates a weighted average from all these periods. Weighted average allows a heavier influence of the recent data. The calculations will look like this on a timeline. To calculate the baseline for an item for 1 day period across seasons of 4 weeks, we identify specific periods on the timeline. Then we assign weights to each of these periods and calculate the weighted average. Please also note that we skip the most recent period in the calculations. Another baseline function, baseline def, works similarly in terms of periods and seasons. It takes all periods that fit into seasons, calculates a standard deviation, and then calculates how many standard deviations are between the last period and arithmetic mean for the past periods within seasons. The calculation will look like this on a timeline. We calculate the standard deviation value for Tuesday 1 to 4 and then calculate how many these values are between the last Tuesday and the mean between Tuesdays 1 to 4. It's similar to what baseline WMA does, with the only difference that it doesn't calculate weighted average but rather checks deviations. Here is a couple of examples of how baseline functions can be used in triggers. The first one checks if the system load for the previous hour is too far from the same hours over the period of 10 days before yesterday. If it exceeds 3 standard deviations, then the trigger fires. The second example shows the trigger that checks if yesterday's web traffic is twice as high as the weighted moving average on the same weekdays over the last 12 weeks. So the range of applications spans from some low-level system metrics such as CPU utilization up to higher level measurements such as web server request or business metrics where calendar periods are especially important. Even though the new baseline functions are relatively simple and easy to work with, there is a couple of points to keep in mind. First, baselines sort of remember problems. If you had some accident that resulted in abnormal values, these abnormal values will be included in subsequent calculations until the season advances past the accident. Time units are not interchangeable. 7 days is 7-day seasons, not one season of 1 week. Before we finish, let's go through some basic technical considerations. These are not specific to baseline and anomaly functions, but rather apply to all functions working with trends. Do not forget to maintain reasonable trend storage intervals to match your periods in triggers. Since Zabbix 5.4, all trend calculations are cached. Don't forget to set a reasonable trend cache size. You can use internal item Zabbix tcache to monitor the performance of your trend cache. If you happen to use these functions in calculated items, please set reasonable update intervals to reduce system load. For instance, there is no point in updating your item every 15 minutes if the most recent period of your calculations is yesterday. Both baseline and anomaly detection tools cater to similar applications when one aims to build resilient alerting in the fast-paced and dynamic environment. Both tools work with trends and thus are suitable only for long-term analytics. If you need a quick reaction to the latest value updates, then see functions that work with history. But despite the conceptual similarity, both techniques attack the problem from slightly different angles. Anomaly STL is a little bit heavier on the system resources, just because there are more calculations to do. Anomaly STL looks for the points that are too far from the majority, whereas baseline functions do calculations for a sequence of calendar periods. So that's it about the new analytics functions in Zabbix 6.0. We hope that these tools will find a good place in your monitoring tool belt. Thank you.
Thank you for a very detailed explanation. I think it will be useful for everyone for months or even years to come. This was very helpful, but we do have a couple of questions. Not simply about these new functions, but trigger functions and history functions in general. So, how often are trigger functions calculated? Specifically, what happens if you combine trend with history functions?
Trend functions, if you in your trigger, if you have multiple trend functions, then Zabbix will select all periods and will choose smallest one to schedule all these functions for calculations. So, for example, if you have like one trend function which works with days and one trend function which works with hours, then this trigger will be rescheduled every hour, but not less, obviously. And as for combining with regular history functions, you can do this. It will be rescheduled every time when these history functions needs to be recalculated. For example, when new data comes in, and the result of trend calculation will be taken from the trend cache. So it should be okay.
Thank you. Next up, about seasonality. So what is the best practice when defining seasons? Should we always use days or hours or weeks? How can we decide what is the best for us?
Well, yeah, that's a good question. You cannot use seasonality less than 1 hour, and 1 hour is also just given that all trends work in terms of hours, not minutes or seconds. You should be okay if you choose any period that is greater than hour. And typically for like low level items which get some system metrics like CPU utilization, like some memory parameters or disks, you can start with 1 day and it should be okay. For business level metrics, you may want to look into longer periods where this seasonality is typically can be in terms of weeks or even months. So something like this.
Okay, I think that clears things up for many people that maybe decide to use this for both of these types of metrics. Yeah. So thank you a lot. This was very, very useful, and thank you for answering the questions, and hopefully we will get our hands on this new functionality very soon. Thanks.
Hopefully, yeah. Thank you.